All right, howdy, and welcome to the Math 470 recorded lecture. So today I'm going to be talking about collision theorems and Pollard's row method. So I'm going to start with the collision theorem that I was kind of getting at last class. Remember that we're interested in the birthday paradox, which is a fact that basically if you have a decent number of people, long before you have 365 people, you're likely to find two that share a birthday. Now, what we're going to be talking about first is a simpler collision theorem than that. So it is this one. Basically, we have an urn of n balls, big N, of which little n are red and big N minus little n are blue. Now, Bob randomly selects a ball from the urn and replaces it in the urn, randomly selects a second ball, replaces it, and so on. He does this until he has looked at a total of m balls. Now, the first statement here is that the probability that Bob selects at least one red ball is this quantity. 1 minus 1 minus n, little n over big N to the m. And then what we have right here is we get a very effective lower bound for this probability. So this effective lower bound is based on the following observation that I proved last class, which is that e to the negative x is greater than or equal to 1 minus x for x greater than or equal to 0. So this is a simple calculus result. And now what we're going to do is we're going to apply it to the first inequality, the one we prove in part A, to get the second one in part B. And the cool thing about the one in part B is that it allows us to make the following observation, which is that if n is very large, and m and n are both, not too much larger than big N, then this gives us a very tight bound. In fact, it is almost an inequality. So let's start with the proof. So the proof goes as follows. We can understand the probability of at least one red by understanding that it's equal to 1 minus the probability of all blue. Now here we're using the fundamental fact about probability, which is that the probability of A plus the probability of A complement is equal to 1. But in this case, the probability of A complement, which is all blue, is easier to compute. Because first off, let's think about what our sample space is, or our outcomes. Our outcomes correspond to a sequence of balls. So outcomes would be something like this. This would be a sample outcome. Blue, blue, red, blue, blue, blah, 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 blah. And then eventually you end, say blue. And the number of balls chosen is m. So there would be m entries here. This is what a sample outcome looks like. So since we're giving all outcomes equal weight, the probability of all blue can be easily computed. And it can be computed basically based on the observation that anytime you draw a ball from this urn, well, let's see what portion of the balls are blue. Big N minus little n. So big N minus little n over n, big N, is the ratio of blue balls to the total number of balls. And so we can think of this as being the probability that when you're selecting a ball from the urn, that's the chance that it's blue. So since we have to make m choices, and each of these choices are independent because, we're always putting the ball back inside the urn, this ratio never changes. So the probability that it's all blue is going to be equal to big N minus little n divided by big N raised to the m. So, simplifying just a tiny bit, this is the same as 1 minus 1 over little n, let me fix that. Little n over big N, all raised to the m. Now we can go up here and we can use this relation. And this relation tells us that the probability of at least one red is equal to 1 minus little n over big N raised to the m. So this completes the proof of part A of the theorem. Now, let me make a new slide right here. Make a couple actually. Part B is going to use the observation that since 1 minus x is less than or equal to e to the negative x, then we also have that 1 minus x to the m is less than or equal to e to the negative x times m. Now we can flip this inequality a little bit by subtracting this from this side and this from this side, and add 1 to both sides to get 1 minus x, all raised to the m, is greater than or equal to 1 minus e to the negative x times m. Now let's substitute in x equals little n over big N, and we get from this 1 minus 1 over little n over big N, all raised to the n, is greater than or equal to 1 minus e to the negative little n times little m divided by big N. And this completes the second part of the proof of the collision theorem. Now we can make some observations about it. If, say, n is equal to maybe 5 times the square root of n, and m is equal to 5 times the square root of n, then, well, we see that the probability of at least one blue is going to be greater than or equal to 1 minus e to the, say, negative 25. And then because the square root of n is getting multiplied by the square root of n, you just get n and it cancels out with the n in the denominator. Now e to the negative 25 is a very, very small quantity. So in fact, I mean, we can go to Wolfram alpha and see 1 minus e to the negative 25 as you can see, this is very, very close to 1, which means with extremely high probability, you're going to find a match. In fact, we could even change this a little bit. If 5 is too big for us, we could replace the 5 here with 2. And now it just becomes, 1 minus e to the negative 4. But even then, this is going to be very close to 1, if not as close. So you can see that you have a roughly 98% chance of finding a match. So this is the first collision theorem. Let's try to explain how it's useful. So let's go back to baby step, giant step. In baby step, giant step, what you do is you have G, which is a primitive element, of Fp, the field with P elements. And you're interested in solving the problem, the discrete log problem, g to the x is congruent to h mod p. Well, what you do is you set little n to be equal to, and let me, I guess, maybe differentiate that because it looks too much like an h. You set little n here to be equal to the square root of p minus 1, and then you take the ceiling of it, and you try to find x by writing x as q times little n plus r. And so you're left with g to the qn plus r is congruent to h. Well, in order to solve this, one thing you can do is you can move part of this power to the other side. And so you can get g to the r is congruent to h times g to the negative qn. And now you've changed the problem a little bit, because the key observation here is that both q and r can be understood as being less than n and greater than or equal to 0. So you have to consider two lists. One list is G0, G1, blah, 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 all the way up to G to the n. And the other list is H, G to the 0, H, G to the negative n, blah, 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 all the way up to H, G to the negative n squared. And in list 1 and list 2, if you can find two matching elements that evaluate the same thing mod p, then you can use this to find a solution to the original discrete log problem. This is the baby step, giant step algorithm. But now the first collision theorem right here can be used to give a different version of it that's probabilistic. And the way this works is as follows. So, if we consider the urn to be the set of numbers Fp star, then we have two different ways of drawing from it. So here's how it goes. What we do is we start, so this will be step 1, I guess. Start by choosing let's choose a constant times the square root of n, random integers, and compute g to the ri, and I'm calling these random integers ri for each of them. Then label these integers blue. So after labeling them blue, we can then label every other number red. Actually, hold on, let me think about this. No, let's label them red and we'll label every other number blue just to be consistent. Label every other number blue. Now, we have another way to randomly choose integers in the urn, which is that we can also, after we've labeled everything in FP star by a color red or blue according to this first procedure, in the second procedure, we can attempt to draw integers or elements of FP star at random by choosing random integers. So choosing randoms, we'll call these Qi, and computing h times g to the negative, so this is going to be the same little n as before when I was talking about Shank's baby step giant step, times Qi. Now, because we're drawing from a random urn, and everything in the urn has already been colored, then we can apply collision 1 theorem directly to deduce that if we're choosing enough Qi's here, say also around c times the square root of n, then we're very likely to find a solution to the discrete log problem. Because all we need at that point is we need the little Qi and we need the little Ri corresponding to a matching pair. So this gives us a probabilistic modification of Shank's baby step giant step. Now here's the issue with it. The big thing is that the original algorithm, the one I reviewed right here, is completely deterministic. And the one right here is probabilistic. But they both have the same expected running time. And in fact, because you have to keep track of the colors, they both require the same amount of memory. So the answer to the question is what is gained is very sad. Nothing. So that's unfortunate. However, there is an upshot. And here is the upshot. By using a different collision algorithm, we can solve the problem using almost no memory. But this is really tricky. So in order to kind of outline how this is done, first we have to describe the other collision algorithm, which is more closely related to the birthday paradox. And then we have to describe the apparatus that's needed to prove it. So let's move on to the second collision theorem. And this one's a lot more interesting than the first. So I have it framed a little differently here. So imagine that you have n people with k keys. Imagine like k passwords or something. And every person can select a key or a password from this list of k total keys. Then the probability that two people have matching keys is approximately e to the negative k squared over 2 times big N. And we're going to assume that k is within a constant multiple of the square root of n. So to prove this, let's think about it. So the proof starts like this. We're going to take the same basic technique we used for the last collision theorem, which is the probability of A complement plus the probability of A is equal to 1. And so we'll start with the probability that at least 2 people share a key. And we can re-express this as 1 minus the probability that everyone has a distinct key. Because somehow asking for everyone to have a distinct key is an easier probability to compute. So as before, let's consider the outcome space first. So outcomes. Every probability space has an outcome, or every probability space has a space of outcomes, and the first thing we should do is look at the structure of those outcomes. And we're assuming every outcome is equally weighted. So an outcome looks something like this. First off, we have n people, and every person is going to have a key. So we might have key 0, key 1, blah, 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 all the way up to k to the sub n minus 1. So we have n total keys. And we're going to be assuming that that n here is smaller than k, just to make it interesting, because if there's more people than there are keys, there will of course be a collision by the pigeonhole principle. So if everyone has a distinct key, then what we're asking is that ki is not equal to kj for any ij. So let's start by computing this probability. So first off, let's imagine that the person with the key 0 here is Bob. And so let's imagine Bob chooses his key first. Well, Bob has k total choices to draw from. And so he can select any key with probability 1 and know that it's not used by anyone because he's the first person choosing it. So it would be k over k. He has no obstructions to his choice. But now the second person choosing a key is Alice. So Alice, well, she can look at all k keys, but now there's one that she has to avoid, the key that Bob chose. So she has k minus 1 choices to make. And so the probability that she chooses one of them is exactly k minus 1 divided by k. And now the next person after, who chooses k2, let's say that's Steve, has to choose a key that dodges whatever choice that Bob and Alice both made. So he has k minus 2 choices. And so the probability that he selects one of those k minus 2 keys is basically k minus 2 divided by k. And you can see how the pattern goes. And you keep going until you get to k minus n minus 1, all divided by k. So this is the quantity of interest to us. Unfortunately, it's kind of a tedious quantity to analyze. So let's start with some simplifications. First off, it's clearly the same thing as 1 times 1 minus 1 over k times 1 minus 2 over k times blah, 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 1 minus n minus 1 over k. And now again, we're going to use the fact that e to the negative x is greater than or equal to 1 minus x. So this quantity right here is less than or equal to e to the negative 0 times e to the negative 1 over k hold on one second. Yeah, that's fine. Times e to the, hold on one second. I just want to be consistent with something that I'm going to do later. Okay, this is fine. So, e to the negative 2 over k, blah, 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 all the way up to e to the negative n minus 1 over k. Now, the cool thing is that exponentials, when you multiply them, their exponents are additive. So this ends up being the same thing as e to the negative 1 over k multiplied through 0 plus 1 plus 2 plus blah, 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 all the way up to n minus 1. And at this point, we can use a formula for the sum of these numbers, because when you add up 0 plus 1 plus 2 all the way up to n minus 1, this ends up being the same thing, or this thing right here is the same thing as n minus 1, I believe, times n minus 2 divided by 2. Let me just sanity check myself to make sure I did the right version of this. So if I do like 0 plus 1 plus 2, this corresponds to 3. So if I plug in 3 into this, does that work? No, it doesn't. Okay, so I have to readjust this. So this is actually n times n minus 1 over 2. Because now if I plug n equals 3 into this, yeah, I get exactly what I want. So this ends up being the same thing as e to the negative 1 over k multiplied through by n times n minus 1 over 2. And this right here forms our core estimate. Because first off, note that what we've been computing right now is the probability that everyone has a distinct key. And we've bounded it from above. But by bounding it above, we actually bounded the thing we want, the probability that at least 2 people share a key, from below. So the probability that 2 people share a key is going to be greater than or equal to 1 minus e to the negative 1 over k times n minus 1 divided by 2. And in fact, we usually go a little bit further and we say that this quantity right here is in fact approximately 1 minus e to the negative n squared divided by 2k. And this quantity right here is very close to this one, so we don't usually worry too much about it. And this gives us the collision theorem that we were interested in. And let me go back here and correct it. The approximate probability that people have a match should be this, not the thing I originally had. So, wait. Now we got it. Okay. So, let's do a specific example of this collision theorem. So, namely, let's do the birthday paradox. So, how many people are needed before the probability that 2 people share a birthday is greater than or equal to 80%. So we're going to use our formula, which is 1 minus e to the negative n squared divided by 2k. And the number of keys in this case is just the number of birthdays. So k is going to be equal to 365. And we can go to Wolfram Alpha and play with it. So minus something squared divided by 2 times 365. And we'll start with 10. So it's about a 12% chance when you have 10 people. When you have 20 people, you have about a 42% chance. When you have 30 people, you have about a 70% chance. When you have 40 people, you have about an 88% chance. So we've gone a little too high. So maybe 35. Let's think go lower. 35 looks good. So, according to this formula, since 1 minus e to the negative 35 squared over 2 times 365 is approximately equal to 0.81, we see that we need roughly 35 people before we have an 80% chance that 2 people share a birthday. But notice this is a fairly small number of people. It's, far less than the number of people you might naively expect that you need. Because of course, to fill up every single birthday, you would need 365, but already by the time you have 35, you have a pretty good chance 2 people share a birthday, which is somewhat surprising. So, that is the birthday paradox. Now, let's talk about Pollard's row method, which is the first real cool application of probability to cryptography. This is Pollard's row method. All right. So what we'd like to do is we'd like to go back to the discrete log problem thing that we were thinking about. And we would like to fix it so that we don't have to use any memory. If we were to use the algorithm that I outlined here based on collision algorithm number 1, the memory usage would have to be proportional to c times the square root of n. We'd like to get rid of that dependency. So let's start with a warm-up. And this warm-up is basically just an exercise in understanding functions. So suppose f is a function from S to S. And so here, S is a finite set. And little x naught is an element of S. Then we can consider the following procedure. We start with x naught, and then we compute x1. x1 will be f of x naught. So it's like we take our function and we apply it to x naught, and this gives us another x1. And then to get x2, what we do is we take x1 and we apply f to it. So x2 is equal to f of x1, which is the same thing as f of x naught. And likewise, x3 is equal to f of x naught, which is the same thing as simply f of x2. And so you can see the pattern. The way I'm going to denote this is that, for example, x4, I'm going to say is f, and I'll put a circle here in the exponent, which means I'm composing the function 4 times of x naught, and blah, 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 blah. Xk is equal to f composed with itself, k times, of x naught. So I take my thing and I keep iterating applications of f. Let's try to think what this looks like geometrically. X naught goes to x1, which goes to x2, which goes to something else, and then eventually you get to something like x sub k. Now, S is a finite set. So eventually, at some point, you have to kind of go back to something that you've already hit. So this is just because if you imagine every one of these elements, x1, x0, x1, x2, is a different element, well, because our set S here is finite, eventually, simply by exhaustion, you have to hit something that you've already hit again. And so you end up with a pattern like this. You keep going, and then eventually, you have xm down here, and then eventually you loop back onto something. So say this is xn, and let's say you loop back onto xk. Well, once you loop back onto xk, then the next thing after it is, of course, xk plus 1. So once you loop back, you're caught in the loop. It's a cycle. So every function gives rise to basically two parts under this iteration procedure: the tail and the cycle. And you might never return to anything in the tail, but you could return to something in the cycle. To give you a simple example, consider the following function. F of x is equal to -1 to the x. Or actually, -1 to the x. Let me think about this for a second. How can I make this interesting? Maybe I'll do this one. Let's consider z mod 10z. And let's consider the function f of x is equal to 5 times x mod 10. So 6, actually I don't want to do 6, I want to do 3. 3 is more fun. So 3, of course, maps to 15, which 15 mod 10 is 5. And then 5 mod 10 then maps to 25, and 25 mod 10 is 5, so you see that you get trapped at 5. 3 goes to 5, and then 5 keeps going to itself under an iteration. Maybe this one will be better. Let's try z mod z mod 18? 18. So in this case, I'm going to do f of x equals 3 times x mod 18. So I'm going to start with 2. 2 goes to 6. Actually, no, that's a bad one. I'm going to start with 5. 5 goes to 15. And then let's see what happens when we do 45. So 3 times 15 mod 18. So 15 goes to 9. And then let's see what happens when we go to 3 times 9. Well, we get stuck at 9. So as you can see, we have two parts. We have the tail, and then we have the cycle. And this behavior is true in general, although in the cycle itself need not have length 1. The cycles can in fact be longer than that. Let me see if I can get a good example of this. See if I can rig something up. So what if I do 27? No. All right, I'll just leave it for now because I guess I could do something artificial. Here's a very artificial example. So f is going to be a function from z to z. And basically it's going to go as follows. 1 goes to 2. 2 goes to 3. 3 goes to 4. And 4 goes to 1. And everything else goes to the square root, or the ceiling of the square root of n. So let's do a simple example. 100, well, the square root of it is 10, so the ceiling of the square root is 10. And then the ceiling of the square root of 10 is 4. So it goes to 4. But then 4 goes to 1. 1 goes to 2. 2 goes to 3. 3 goes to 4. So this part right here is the tail, and this part right here is the cycle. So even though I kind of rigged this up to work a certain way, this phenomenon does occur in generality. So this leads us to the following definition. So the forward orbit of x naught under f is the set x naught, f composed with x naught once, and then f composed with x naught twice, and then so on. And first off, this will be a subset of a finite set, so of course it will be finite. And we can always express it as the union of two parts. One is the tail, and then one is the cycle. The tail is things that show up once. And the cycle is things showing up infinitely many times. So this is the basis, or at least not the basis, but the setting of Pollard's row method. So let me find the statement, just so I don't have to write it out by hand. So S here is a finite set, and it contains n elements, and f is a function as before. So little x in S is the initial point. Now, suppose that the forward orbit of x has a tail of length t and a loop of length m. So I'll draw this figure in a moment, or in fact, maybe I can just steal it from the book. Yeah, I'll just steal it. Then you have that x sub 2I is equal to x sub I for some I between 1 and the length of the tail plus the length of the loop. And if this map f is sufficiently random, then the expected value of the length of the tail plus the length of the loop is approximately equal to 1.2533 times the square root of n. Hence, if n is large, we are likely to find a collision in O of n steps. But the beauty of this, the real amazing thing, is that you don't actually have to keep track of the entire orbit. All you have to store in memory, if you are implementing something based on Pollard's row method on a computer, is x sub 2I and x sub I, and you keep doing it until you find a collision. So in fact, you could do this with almost no memory at all, which is the real advantage to it. So let's start by proving part A, and then we will look towards a proof of part B. So here's the figure that the book quotes. So what we want to do is we want to understand under what conditions is x sub 2I equal to x sub I. Well, what this means is that in this cycle, they have to differ by the length of the loop. So this means that we want 2I to be equal to I, or rather congruent to I, mod m. Because, for example, if you're here at x t plus 2, then the number of times you'd have to go around to get back to it is m times, because the loop is length m. So really, if you're looking for this equality, what you actually want is you want 2 times I to be congruent to I mod m. But this is the same thing as I being congruent to 0 mod m. So for part A, all we have to do is find the first I, which is greater than the tail, because we don't want something that lies in the tail, that is a multiple of m. So between the numbers t, t plus 1, all the way up to t plus m, well, there's m plus 1 numbers, and at least one of these numbers has to be a multiple of m. And so as soon as we find that multiple of m, then we will have found an x sub 2I that is equal to xi. So that completes the proof of part A. Part B is where things get really, really tricky. So this is going to need the full collision theorem. So suppose f is a sufficiently random function. Well, what do we need? We need to consider the following probability. Recall that I'm taking x sub I here to be f composed I times applied to x naught. And I'm interested in the probability that x naught, x1, all the way through x sub k minus 1 are distinct. I want to find out what the expected size of the tail and the cycle are. And so what this is saying right now, it's really the same thing as the probability that the tail and the cycle starting at x naught has length greater than or equal to k. So I'm going to start by analyzing this probability. And the way I'm going to analyze this probability is precisely by appealing to the birthday paradox, or actually the more general collision theorem. So let me make some things. Because we can think of S as the set of keys, and my notation is going to be a little bit different from before, because I'm going to take the size of S here to be equal to capital N. Then the probability that x naught, x1, all the way through x k minus 1 are distinct can be estimated to be let me see. It can be estimated to be approximately e to the negative k squared divided by 2n. So let me just give one caveat, because this is kind of the issue with the notation I originally had. If you go back up to the collision theorem, I've kind of flipped the role of k and n, because now I have k people and n total keys, but I apologize for that confusion. But really it's the same formula. And the reason I don't have a -1 here is because I'm not asking for them to have something in common, I'm asking for them all to be distinct. Now, because of this, we can also look at the probability, and this is a conditional probability, that xk is a match, granted that x0 through xk minus 1 are distinct. So this is a bit different, because now what I'm asking is that everything from x0 to xk minus 1 are distinct, there's no repeats. But then when you get to the kth element in the list, you get a match. So this is when the cycle appears. So this is actually just the same thing as the probability that the length of the tail plus the cycle has length k plus 1. So, given this, oh wait, no, because it would actually just be length k. Now we can analyze this. The way we analyze it is that we note that we have k elements here, and we have n elements total. So the chance, if our function is random, like we assumed, that our function at the kth element matches with x0 through xk minus 1 is going to be k times, or k over n. This is the number of elements that we already have in our list divided by the number of elements total. So from this, we're able to conclude that the probability that the tail length, or tail plus cycle length, is equal to k is going to be k over n, but also times the probability that x0, x1 through xk minus 1 is distinct, which is e to the negative k squared divided by 2 times n. So, now that we have this, we can consider the expectation of the tail length. This is going to be the sum of the tail length times the probability of the tail length. So k, and I'm going to sum from k equals 0 to whenever, times probability, tail length, or maybe I'll say simply t plus m is equal to k? Well, by what we just computed, this is the same thing as k squared times e to the negative k squared divided by 2 to the n. So we can estimate this quantity by consideration of the following integral. We're going to look at the integral from 0 to infinity of x squared times e to the negative x squared divided by 2 to the n. And in calculus, you learn that this integral is approximately equal to this sum. And by using calculus, you can compute that this integral is itself approximately equal to 1.2533 times the square root of n. Now, in fact, you can compute it exactly if you wish, using some techniques that I don't want to talk about. But from this, we get that the expectation of t plus m is approximately equal to 1.2533 times the square root of n. So, from this, we have estimated the expectation of t plus m, the expected tail plus cycle length. Now that we have this, let's think about how we can modify Shank's baby step giant step. What we can do is we can consider the following function. We can set f here to be equal to gx x squared and hx. And the first one is for x less than p over 3. The second one is for x greater than p over 3, but less than 2p over 3. And then the last one is for x greater than or equal to p over 3, but less than p. Now, what happens here is that, for example, if we do f of 1, we get g. But then if we do f of 1, assuming our primitive root is small, which it usually is because it's usually like 2, 3, 5, or 7, we might get, for example, g times g. But even if we didn't, we would either square it, and we would, by this one, we would get g squared, or we would get h times g. And you can readily convince yourself that f of, when you compose f with itself I times, applied to 1, you can check that you get g to the L sub I times h to the m sub I. And these exponents can be computed. You just have to kind of keep track of them as you go through the algorithm. So now, suppose you find, using Polward's row method, that x to the 2i is equal to x to the I, or x sub I. Then this gives you a relation that g, say, to the alpha times h to the beta is equal to g to the a times h to the b. And you know what alpha, beta, a, and b are because you keep track of them as the algorithm runs through. You can see that, you know, if the third thing is happening, you're adding 1 to the h exponent. And if the middle thing is happening, you're doubling the values. And in this one, you're adding 1 to the g exponent. So if you have this relation, then it actually tells you some stuff. Because what you can do is you can note that if you set u here equal to alpha minus a mod p minus 1, let me fix that. Okay, that's somewhat annoying. I'll just do it up here since I can't seem to get rid of this little thing. If you let u equal alpha minus a mod p minus 1, and you let v equal beta minus b mod p minus 1, then you find that g to the u is congruent to h to the v mod p minus 1. Now once you have this, you're in a very good position, because all you have to do is you can compute that, say, y is equal to v inverse mod p minus 1. And then if you raise both sides to y, you get g u y is congruent to h v times v inverse, which is actually just going to be congruent to h to the 1 mod p, which means u times v then solves the discrete log problem. And all you have to do in executing this is basically just keep track of the exponents at every stage. So this is an example of how Pollard's row method improves on baby step, giant step. It allows you to solve the discrete log problem in a way that doesn't really use any memory at all. And that is what makes it really, really cool. So that's it for this lecture. And I will see everyone on Tuesday.